In this lesson, we're going to go over how to find the volumes of solids of revolution using the washer method or the donut method. So we're going to be finding volumes of solids that are being rotated or revolved around the x-axis or the y-axis. So last time we talked about the disk method, which is represented here on the left, and today we're going to talk about the washer method or the donut method, which is represented on the right. So let's just recap the disk method. So when you have a disk, we have a solid figure, and we can see here that it is a solid. We had a shape that was rotated around, in this case, the x-axis, and it's created this solid. It has a radius of r, and we can see here, right, there's a radius, and it's r. It has a width of dx. So right here, that is dx. Okay, so this cross sections here are circles. So if we wanted to find our volume, we would say that it is pi times the integral of r squared dx. Right? Each cross section is a circle. The area of a circle is pi radius squared. And then because it's the volume, we're multiplying it by the width. Okay, we pulled out that pi since that's a constant, so we can bring it on the outside. Now we're looking at the washer method or the donut method on the right-hand side. So the difference here is that instead of being a solid figure, it is hollow and it has a hole. So it's kind of hard to kind of visualize, I guess, but think of it as pretty much like a donut. So we have a larger radius. There's two different radii. There's an outer radius, which is going to be the radius from the outer part of this figure to the axis of rotation. So that's going to be big R. And then we also have a little r, which is going to be from that second piece to the axis of rotation, and that's little r. So there's really two functions going on here, and there's really going to be a hole in the middle of it. So if you think about it as like a donut, right, there's a hole in the middle. So we have, again, the width of dx, which is similar to the disk method. So when we're writing our volume here to find the volume of this whole hollow section here, we have the cross sections again are circles, but in this case, there's a hole in the middle. So we have the larger circle, which has a radius of big R. So that would be pi times the integral of big R squared dx. And then we're going to subtract from that the area of the smaller cross section that's a circle. So that's going to be pi times the integral of little r squared dx. Okay, so when we take the big circle and we take away the smaller circle, we're left with what's left over. So we're taking out that hole. So another way that we can write this, which is the way that we'll see it more often, is just by writing pi times the integral of big R squared minus little r squared dx. Okay, so we're just taking the bigger radius, subtracting the smaller radius, so the outer radius minus the inner radius, and that would be the area of the circle, then times the width will give us that volume. It's a little bit hard to visualize. So we know how to find the volume of solids that are rotated around the x-axis or the y-axis. But what if the function is not bounded by an axis, but by another function instead? So what we had done before was our functions were bounded by the x-axis or the y-axis. But now they're not, and that's what creates that hole in our graph, which makes this a washer method or donut method type problem. So here we have this function f of x on the top, g of x on the bottom. If I were to rotate this around the x-axis, we're looking over here at part B, we can see that it's going to rotate, but there's going to be the little gap between g of x and the x-axis. That's not going to be part of this. That's going to be where my hole is. So as it's rotating, it makes this reflection across the axis. So it's going to create this 3D shape, but again, it won't be a solid because it has that little hollow hole in the middle. That is not part of our shape. It's a little bit hard to, I guess, visualize and comprehend, but we'll do our best. So let's look at this example. So find the volume of the solid obtained by rotating the region bounded by y equals x squared plus 4, y equals 2, x equals 1, and x equals 3 around the x-axis. So here's my 2D graph, right? I have my x squared plus 4, my y equals 2. It's bounded by x is 1 and x equals 3. Now, if I rotate this around the x-axis, it's going to create this type of like lampshade almost figure where there's going to be a hole in the middle because we can see that it's not flush against the x-axis, that there's a little gap between the line y equals 2 and the x-axis. So the first thing we want to do is obviously identify which axis we're revolving it around. So in this case, it's the x-axis. And then we want to identify our big R and our little r. So our big R, I'm just going to put big R here, that's going to be our outer radius. So that's going to be the farthest one away from our line of rotation. So we're rotating it around the x-axis. So the farthest one is going to be x squared plus 4. So my big R will be x squared plus 4. My little r is going to be the closer one. So that was going to be 2. Okay. So when I go to write my volume, the volume is equal to, I know it's going to be pi times the integral. And because I'm going revolving it around the x-axis, I'm going to be using the x values for my limits of integration. So I'm going from 1 to 3. And it's going to be big R squared minus little r squared. And it's dx because we're, again, revolving it around the x-axis. So here's my initial setup. And typically, if this is like a calculator question where we don't have to do the antiderivative by ourselves, on an AP exam, you can leave your answer like this if they're just asking you to write the integral. So I would actually recommend doing that because if, let's say, you wrote x squared plus 4 as x squared minus 4 for some reason, you wouldn't get the setup correct. So if you want to identify big R as being whatever function and little r as being whatever function, and then when you put it into the volume equation, you can just use big R and little r. Okay, it's just really important that you identify what they're equal to, and then you can just call them as so later on. Okay, but I'm actually going to plug the actual one back in because this is easy enough to do without a calculator. So we're going to do it the harder way. So let's go ahead and keep going. So if I plug in our big R squared, this is going to be x squared plus 4, and I'm subtracting my little r squared. So actually I'll leave this like, oops, squared minus little r squared, put an extra parenthesis around here, dx. Okay, so I'm squaring my big R, I'm squaring my little r. So if I do that, right, 2 squared here, that's 4, and then here I have to FOIL this out. So yes, it is more annoying to do this by hand, but it's not anything that we can't do. So 1 to 3. So this is going to be x to the 4th plus 8x to the 2nd plus 12 dx. And now we can just use the reverse power rule. So I'm going to have that pi on the outside, and then I will get 1/5 x to the 5th plus 8/3 x to the 3rd plus 12x. And then I'm just evaluating it from 1 to 3. So I need to plug a 3 in and plug 1 in and subtract them. So if we do this correctly, we should end up with 2,126 over 15 pi. Okay, let's look at another example. So I tried to pre-draw this because I knew how bad my drawing was last time. So we'll just look at that. So the area between the curves y equals x and y equals x squared is rotated around the x-axis to form a solid. What is the volume of that solid? So if we look here, let me try to highlight this. So right here, that's y equals x, that straight line. And then in green here, I have y equals x squared. Okay, so if I take this image and then I rotate it around, again, the x-axis, okay, we can see that the reflection is going to be this piece over here below it, and that we are making these circles that are our cross sections, and there's going to be a hole cut out in the middle. So again, we want to first, I guess, identify what our big R is and what our little r is. So if we look at our picture here, big R, remember, will be your farthest, the function that's farthest away. So my big R is going to be x. My little r is going to be the one that's closest to my axis of rotation, so that would be x squared. Okay, so when I go to write my integral, I have pi times the integral. Now I need to know what my limits of integration are, so I need to know where these are intersecting. Okay, so we can take our original functions, x and x squared, and we can set them equal. So here we end up with x squared minus x equals 0. I can factor out the x, so I get x minus 1. So when I solve this, I get 0 and I get 1. So my intersection points, if I plug it back in, I get 0, 0, and 1, 1. Since I'm going around the x-axis, I'm going to use the x values. So my lower limit will be 0, my upper limit will be 1, and then I have big R squared minus little r squared dx. And again, these are easy enough to do, so I'm going to actually keep going and just plug the values back in. But again, if they're more confusing or you're using your calculator, just identify big R and little r and just leave this as your answer that I'm asterisking. Okay, so that would be the setup. I'm just going to plug in big R squared, so that's going to be x, and I'm going to square that, minus little r squared, so little r is x squared, so if I square x squared, I'm going to get x to the 4th, and then dx. So from here, I can again take the antiderivative, so this will give me 1/3 x to the 3rd minus 1/5 x to the 5th, and then I need to plug in the 1 and the 0 and then subtract them. So if we do this properly, we end up with 2 pi over 15. Okay, and let's look at one more. So here again, we have the same exact picture. We have x and x squared. So I'm going to just kind of highlight this again. So here is our original function, that's x. And then we have x squared, which is this piece. But in this case, we're now rotating it around the y-axis. So now we're flipping it this way, and you can see the reflection of it over here. And again, we are making these cross sections that are circles, and the middle piece is going to be cut out as our hole. Because we're going around the y-axis, we want to make sure that our functions are in terms of y instead of x. So I have y equals x was my original function for this first one. If I solve it in terms of y, I get x equals y. All right, so that one wasn't very hard to switch. If I have y equals x squared and I want to solve it for x, I'm going to get that x is equal to the square root of y. So now when I think about big R and little r, big R, again, is going to be the farthest from the axis of rotation. So I'm rotating it around the y-axis. I'm just going to draw a little dotted line here. So my farthest function is going to be the farthest right function. So I want it to be the farthest from my line of rotation. So that is going to be the square root of y. And then little r is going to be the closer function to the axis of rotation. So that's going to be y. Okay, we already found the point of intersection on the previous problem. So we know that it was 0, 0, and 1, 1. So when I go to find my volume here, I'm going to set it up as pi times the integral. My lower limit here is going to be the lowest y value, which is 0. My upper limit is going to be the highest y value, which is 1. And then we have big R squared minus little r squared. But now the width is going to be dy because we're doing this in reference to the y-axis. So now again, I'm just going to plug it in because it's easy to do by hand. So the integral from 0 to 1, so big R squared, so big R is square root of y. If I take the square root of y and I square it, I get y. Little r is y. If I square it, I get y squared. And then again dy. So I can then take the antiderivative. So I'll get 1/2 y squared minus 1/3 y to the 3rd. And then I'm going to evaluate it at 1 and 0 and subtract them. So if I do that properly, I should get that the volume is equal to pi over 6.